right, welcome. Welcome, everybody. Please close your laptops. Thank you. Okay, so we talked about support vector machines. And the idea behind support vector machines on a high level is quite straightforward. Is the mic on in the back? Can you hear me? Mic is on. Okay. So we have, once again, two classes, positive and negative points. And we started out with the question that we have an algorithm to find as a hyperplane between those. That's the perceptron. But the perceptron just gives us a hyperplane. And it would be nice if you could actually find a particular hyperplane, ideally one that's well suited for classification, right? So, and in some sense, it comes with the realization that some hyperplanes may be better than others. You could have a really bad hyperplane, for example, this one here, right, would actually classify this correctly, but if any test point, were here, it would actually classify that as a cross, which seems intuitively the wrong thing to do. Right? And so the idea behind support vector machines is that a hyperplane is good if it maximizes the margin. So, or the best hyperplane is the one that actually maximizes the margin, where margin is defined as the distance to the closest point. Now, of course, it has to be a hyperplane that separates the two data sets, so it has to be in between these two. And then actually it turns out that the one that maximizes the margin always has equidistance to the closest point from one class and to the closest point of the other class. Right? That must be the case, otherwise you could move it closer. And, well, that doesn't really seem like it's in the middle, but yeah. So that's the idea. So the question was, how do we find this hyperplane that has maximum margin, maximum distance to both sides? And what we did is we defined the definition of margin, and then we just said, let's maximize this subject to the constraint that every point is on the right side of this hyperplane. So if this here is W, these here must be on the positive side, these must be on the negative side. So this was a constrained optimization problem. And that was kind of ugly, so we had to do a little bit of massaging. And ultimately, we ended up with the following optimization problem, which is equivalent in the final solution. We minimize the square of W subject to the constraint. This means such that for all I, yi, W transpose xi plus b is greater or equal 1. And that is the SVM optimization problem. So the constraint here says every single data point has to be at least a margin of 1 away from the hyperplane. It must be on the right side. Because that's positive. It must be at least 1 away. And what W does here is tries to make W as small as possible. So you have to be careful. 1 here is actually really just 1 unit, right? It doesn't mean anything because you can divide W and B by a constant, right? So by actually minimizing W, what you get is basically the smallest W. That means such that these are actually this is actually the case. So ultimately, what it does, it basically tries to find the hyperplane that pushes them away as much as possible everywhere. So, and we had this little exercise where we basically looked at the two different formulations, and we could show that they are the same in the optimum. Right? So beforehand, we actually had a bunch of constraints, but we showed that actually, at the optimal solution, that's equivalent to these constraints here. So we can just enforce these constraints here. Just to, I guess in some sense, the way this is like, basically we have a set of all possible solutions that satisfy the constraints, and here we have the optimal. And what we showed is that actually there's another set of solutions that has the same optimal. So that's basically the smaller set is the set of constraints. If you remember what we did last time, those were the two basically different formulations. Okay, anyway, so this is the SVM optimization problem, and some people asked me afterwards, like, wait a second, what if such a hyperplane doesn't exist, right? So what if, for example, for example, we had one circle here or something like this, right? The perceptron would loop forever. What would happen in this case actually, if you optimize this, if you stick this in a quadratic programming solver, what you would get is actually an output infeasible. Right? There's no feasible set. There's no single point that actually satisfies the solution. So a natural question is, well, in this case, right, is it really the right thing to say, well, I'm throw my hands up and say I give up, or should I maybe still output something that's reasonable that separates most of the points? And that's, of course, something people thought about, and actually this was published very soon after the original SVM formulation came the formulation with slack variables. And so the idea is basically the following. You say, imagine I can't possibly solve this problem. Right? This, for example, here we have some points, like, here there's no hyperplane that satisfies these points from each other. What do I want in that case? And the formulation that Corinna Cortez came up with was, she said, well, in this case, I still want these to be satisfied as much as possible, but I allow for some violation of these constraints. And how do you do this? You basically say, okay, what I'm doing is I add a little bit of slack here. And I call this xi. And these xi must all be greater or equal 0 for all I. So this xi here basically says this is something that I'm subtracting from 1, right? And then I can always make this satisfied, right? Like whatever this value on the left is, I can always subtract enough on the right such that this constraint is satisfied. Does that make sense? Raise your hand if that makes sense. Okay, so one more time, basically I have this constraint, I can't satisfy it. This here on the left-hand side is just not greater or equal 1, right? So what I do is I say, well, I just subtract something from the right until it's satisfied. And what I want to do is I want to subtract as little as possible. So what I'm saying, in addition to minimizing W squared, I'm also minimizing the amount that I'm adding. And that's the formulation. So this is called SVM, the soft constraints. So it basically means you should satisfy all these constraints, but if not, well, then you just have to pay for it, right? So you basically have to, assign some non-zero value to xi. That costs you here in the objective. So you will get a lower objective value, right? So whenever it's possible, the optimization will try to find a hyperplane where all these xi's are 0. But if it's not possible, for example, in this case, it says, well, this guy, for example, just has some non-negative xi, and there's nothing I can do about it. Non-zero xi, and there's nothing I can do about it. Any questions? Yeah?
Why are you weighting your errors with a constant? Like, why would you ever use a weight other than 1?
Oh, why would you ever use a weight other than 1? Good question. So, well, because these are in some sense totally different units, right? And so sometimes you may really, really care. So let me show you the following example, right? So if I allow this amount of slack, right? Here's something that could happen, right? Imagine I have some points. It doesn't look quite as drastic like this, but it looks like, something like I have a circle here, right? What the optimization problem may say is, well, this is only just one of many, many, many points. Let's say I have many, many, many points, right? And I can actually get a much, much larger margin overall if I place the hyperplane here and just sacrifice this one sucker, right? And so if you allow this or not depends on how large your C is. So if you crank up your C a lot, let's say you make it like, you get it close to, infinity, then it would never do this, right? Because this one point would, the cost would be so large, it wouldn't be worth it, right? But if you relax this, then actually, eventually basically, in the extreme case, if this is 0, then you're actually saying, well, it doesn't matter at all, right? And then it just, sets all the xi's just to negative, to the value here, so that actually, it doesn't care at all about getting points anymore. And if you make it small, then it would say, well, let's just sacrifice some points just so we get the maximum margin. And that is important if you suspect that your data may have mislabeled data points, right? So for example, if you think like some of my data points are pretty noisy, right? And I'm not even sure, but in biology, often that's the case, or in applied sciences, where you say, well, say I classify certain, proteins or something, and it's just not an exact science, only 80% of my labels are correct, then you would actually assign a small c here because you just say, well, I have to allow some slack, right? And what I really want is the general trend. Does that make sense? Good question. Good question. Any other questions? Yeah. Yeah, so is there a good rule of how to set C? And the answer, yes and no. So C is what we call a hyperparameter. It's not a parameter that the machine learning algorithm learns, it's a parameter that we are setting as the user. And that's kind of your intuition about the data get put in here. Often what people do in practice is they take a training data set, they take a holdout set, so a validation set, they train on with multiple values of C on the training set, and they look at the error on the validation set. And they pick the value of C that has the lowest error on the validation set, and then they retrain on the union of the two sets. And typically that works in two steps. The first thing is actually, you try to get the order of magnitude right. So what you do is you try like 10 to the minus 4, 10 to the minus 3, all the way to maybe 100. And you look at which one is best. Then you explore around that order of magnitude. Let's say 0.1 is good. Then you maybe try 0.2, 0.3, 0.4, 0.5, and maybe 0.09 and so on, right? So that's called a telescopic search. So you first look at, just the order of magnitude, and then you zoom in and look again in that order of magnitude. Very good question, yeah. Any other questions? All right. Okay, so now we have this optimization problem with these xi's. That's still a linear problem. We still only have linear constraints, and this here still remains a linear problem. So we can just stick that in a quadratic programming solver. We can actually also do something else. And what we can do is we can basically say, well, given this, right, I know that the size will always be as small as possible, right, because I'm penalizing them. So I can actually solve this for xi, right? So and what I can do is I can basically rewrite the loss function as the following. Well, let me actually first divide this. So basically, what I can say is, well, in some sense, I know what xi is, right? So xi equals is either 0 if yi w transpose xi plus b is greater or equal to 1. Right? If the constraint is naturally satisfied, the optimization problem will always put a 0 on xi because it has to pay for it. And otherwise, it's less than 1, then we can also solve for it, because then we can just say, well, in this case, xi equals 1 minus yi w transpose xi plus b. Okay, any questions? Alright, so basically we're saying, well, what does the optimization problem do with xi? Well, if this constraint is naturally satisfied, it will set it to 0. So if the constraint is satisfied, it sets it to 0. If it's not satisfied, then actually basically has to make up for the margin, right? It basically says this point is not 1 away, so what it has to do is has to make up for this margin. That's what xi is, right? So that's basically what xi is assigned to, and that's exactly, we can just solve for that directly, right? So xi must be the following value. It would never set it any larger, because then it would pay for, pay extra. Raise your hand if that makes sense. Okay, good. So if we know this, then we can actually just stick the xi's, wait, damn it, I never noticed, into the objective. So what is our objective? Our objective is minimize over W and B. And then we have W transpose W plus C times the xi's, C times the sum over all xi's. But we know exactly what xi is, and that is, it's the max of 1 minus yi w transpose xi plus b, comma 0. Yeah? We are not. We are not anymore. We've given up on that. So that's correct. That's correct. But you're paying for it, right? So in the objective function on the very top right, you actually you're summing over all the values of xi, and you're trying to minimize that function. So whenever possible, we try to make psi as small as possible, right? So what you're describing would exactly happen when you have the scenario that has, over here, basically one circle is up, with the crosses, and it basically just sacrifices that one, right? So if you have an outlier that's mislabeled, for example. Good question. Okay, so let me just make this clear. So this psi I is 1 minus y, either this expression on the, or 0. And if you think about it, that turns out to be exactly the max of 1 minus yi, and this here is the prediction with 0. Do you want to spend, maybe I give you one minute, you and your neighbor, please discuss why this here is correct. All right, any questions? Yeah?
So what if the right side of your max function is some larger than 0 but less than, like if the negative sign chunk is less than 1 but greater than 0, so you have a very small positive number, you would end up getting back to your error even though the inside was still positive and therefore it did the right classification?
Yes, that's right. That's right. So what he's saying is, what if this term here is what if this term here is not greater or equal 1, so it's not 0, but it's greater or equal 0? Right? So then in some sense actually, this here means we are classifying correctly. If this is greater than 0, that means we are classifying the point correctly. But if it's not greater than 1, then we are still paying for it. And so what setting is that? That's this setting, right? Where you basically have, these are my points. This is the hyperplane. Here's my margin. And I have one outlier that's here. And it's basically too close. Right? It should be outside the margin of 1, but it's not. So I'm paying for that one. That's basically what it is. Okay, any questions about this? Is this clear? Raise your hand if that's crystal clear. Okay, good. All right, so this is very, very nice now. Because what does that mean? This here is actually just a loss function. And this here is what we call a regularizer. And if we just have a loss function of our W, we can just do gradient descent. Right? So we don't actually have to go to the math department and get the QP solver. We can just actually look at this optimization problem. There's it's almost differentiable everywhere. It turns out if you square it, then it becomes differentiable. So you can do that. Some people do this. And now we can just use gradient, ideally technically correct, subgradient descent, and just optimize this, and it's just like logistic regression. Any questions about this? All right. Unfortunately, I don't have my laptop here today. I have some technical difficulties, but I can show you. You can just look at the figure that's in the printout. All right, so this is also on your sheets. What I'm showing you here, and I hope you can see this, this here is a data set of, a binary data set of crosses and circles. And the one thing you notice, like this data set is kind of especially designed such that basically the crosses are all here, the circles are all here, and one little circle is kind of this outlier, right, lies here. And so so this is linearly separable. And if we set our C to be large, we set C to 100, then what it does, it really penalizes any slack. So we'll try to find a solution with 0 slack. And that's exactly what it finds. So what you see is here, this black line is the hyperplane. And the white line is basically exactly the margin of 1. Okay? And it draws the margin, basically it scales the hyperplane exactly and positions it exactly such that the closest crosses here lie on the margin of 1, and the closest circle lies on the margin of 1. And now one thing you can do is you can actually solve this again and reduce your C, right? So if you basically now, maybe you're starting to suspect that your data set maybe is a little noisy, right? And maybe that point actually should be a cross, right? Who knows, right? Seems a little suspicious, that one point. So if you now lower your value for C, what happens is you can see that now I'm reducing it to 10. That's still basically the same thing. You can see the white line is actually a little bit outside of it. So this circle is now inside the margin. If I lower it to 1, what does it do? Now it's allowed to assign a little bit of slack, right? I'm giving it in some sense a slack budget. That's how you can see this. And what it does, it assigns the slack to this point here and to these points here, right? So it moves the hyperplane more in the middle. And you see this guy here is still classified correctly, but it's really, really close to the hyperplane, right? So that incurs some cost, but it's willing to take it because it doesn't have to pay that much for it anymore, right? So C is basically by how much we multiply the slack variables. Does that make sense? Raise your hand if this makes sense to you. Okay, awesome. Now we can go even further. We can say, okay, well now, we're going, this is a sale, right? This is like, slack variables become really, really cheap, so it can allow a lot of slack. And what's happening is, you see here, it actually puts this hyperplane smack in the middle, right? So on average, you have very little slack, but it doesn't care about these 3 points and these couple points here. Okay? So what it does, it actually is more concerned about having a large margin, right? And less about getting every single point correctly. And then if you do this even further, at this point, actually, it assigns a really large margin. You see W is tiny now. This here is my little W, right? So the margin is very, very large. And in fact, every single point lies inside the margin, right? So in some sense, the point of the margin, is no longer, in some sense, the point of the margin is that it separates two classes. So in this case, I would say the slack variables, it's too cheap, right? It kind of overdoes it a little bit. All right, so that's basically the effect. So as a practitioner, you have to find, you as data scientist, your job is to find the right C. Any questions about this visualization? Yeah?
So the white lines represent like the margin with the slack?
So the white lines is exactly the line of, every point that lies there has exactly a margin of 1. There's basically a distance of 1 from the hyperplane. Right? So y w transpose x plus b is 1 in that case. So, and that's what we want, right? So that's basically, we want all the points to be outside of here, right? So in some sense, the idea really is that you want this solution here, but you're allowing it to basically mess it up a little bit if that's too strict. So, probably, if you were actually concerned about this data set this year, I would guess gives you the best test error, right? Because probably this here is an outlier, this one circle, and probably most of your circles lie here, most of your crosses lie here. So having the line here in the middle is probably, going to generalize the best, right? The danger here is with this solution is that it's actually quite likely that another cross could end up somewhere here, and you will misclassify those, right, during test time. That's the idea. Any more questions? All right. Okay, so then we are moving. This here, in some sense, is the perfect segue. So if you look at this is exactly the setting that we looked at when we talked about gradient descent. Right? We basically said, what if you just have a function? This here is my function that I'm minimizing, and this is a function with respect to w. Right? And I'm trying to find its minimum while we use gradient descent or second order methods, etc. And it may be surprising that this SVM, that we started out with something very, very, with intuition, we want to find the maximum margin hyperplane. Then we derive this quadratic program formulation, and it turns out we can even write that as a loss function, right? So in exactly this form that we can use with gradient descent. Similar to logistic regression. And as it turns out, a lot of machine learning can be written in exactly that format. So very, very often we can just write it. Ultimately what it boils down to is, even if you come up with a probabilistic intuition or with some, for example, here is like this a geometric intuition, you end up with some function that you're trying to minimize. And typically, this function has two terms. One that we call the loss, and the other one that we call the regularizer. And the properties of these two are that the loss function typically involves x, y, and w. And what the loss function measures is how many mistakes you're making. So this function here is large if you make many mistakes on your misclassifications on your training data. Whereas the regularizer does not involve the data typically, and does not involve the labels, just involves the parameters you're fitting, just involves w. And what the regularizer tries to do is tries to penalize overly complicated answers. Right? In an SVM, that translates exactly into finding the maximum margin hyperplane. But if you take a step back, actually, it turns out that this is exactly what you discover in many machine learning algorithms. And the idea is basically the following. You have a balance between, do I want to get every single point right on my training data? Or do I want to get a simple solution? Right? And there's a principle called the Occam's razor principle. There's actually a specific term in learning theory, but ultimately, if I just paraphrase it, the idea is, what typically the simplest answers tend to generalize the best, right? So you can come up with really, really complicated answers that work on your training data, but often then actually you're doing something that doesn't work anymore in the general case. So what we would like to do is try to find an answer that explains our training data and is as simple as possible. And in this case, simplicity is measured by the norm, the squared norm of our W vector. Turns out that translates into having a large margin, if you think of it from the SVM perspective. But you can also just think of it in terms of just plain, small norm is a simpler answer. Okay, and any questions about this? So this means that what we typically do, the way we typically write this, is we try to minimize some W are our parameters, minimize some loss function of W plus some regularizer of W. And this here is some lambda. And actually, sorry, let me just write this, make this more clear. The loss function also goes over my data point. 1 to n, loss function over, and how did I write it? I wrote HW of x, comma yi. So what's HW here? HW is the predictor. Given my W, I have the following classifier for every single x. And my loss function basically measures how close am I to the true label. Right? And I sum over all my data points. Often you have a 1 over n here. And here you have the regularizer of W. Regularizer measures the complexity of your solution. Saying like, did you find a really, really complex solution or did you find a simple solution? And usually this is large if you find a very complex solution. Lambda trades off between the two. Here we have a C, but one thing we can do is we can just write lambda equals 1 over C, then we get a lambda here and a 1 here. Right? And then it's exactly this format. This here is my R of W, and this here is my loss function L. Okay, and we saw exactly the same thing when we did logistic regression, where we also actually had the loss function, which was basically this log loss, and the regularizer when we did map estimation. Then we actually got, once again, W transpose W as the regularizer. Any questions? All right. A lot of theory of machine learning is built up on top of this framework, which we call empirical risk minimization. So the idea is, well, really what I would like to minimize is this loss over my test data. I can't do this. So what I do is I minimize this loss over my training data. I will be overfitting, so I'm adding this regularizer to favor simple solutions. And we will see many, many examples as the course continues now of exactly this framework. So one thing I would like to do today is give you a little overview of a few loss functions that are quite popular in machine learning that fall exactly into this paradigm, and then maybe next lecture we will move on to the regularizers. Okay, so this here is our framework. We basically want to minimize a loss, and we also have regularizer. For now, we just care about the loss. And the first loss that's quite popular is actually one that we just looked at, and that's the hinge loss. So we call this hinge loss. And the hinge loss is basically just max. And that's exactly what the SVM does. 1 minus HW of x times yi, comma 0 to the power of p. So this is exactly the loss function that we had earlier here, where HW of x was thus W transpose x plus b. That's my h of x. So I'm writing this as h of w because it doesn't have to be a linear classifier, actually. So later on in this class, you will have nonlinear classifiers where the decision function is more complicated, but we can actually use exactly the same framework. Right? So I'm just making it a little bit more general in this case. So if we have p equals 1, that's called the SVM. If p equals 2, and that's the squared loss SVM. And the reason people sometimes use the p equals 2 is because then it's differentiable. So some solvers only work with differentiable losses. And also actually, it turns out actually you can actually find a closed form solution in that case, actually, because it's parabola. Okay, another loss that we've already seen is the log loss. And that's as follows. The loss is log of 1 plus e to the minus yi hw of xi. And this here is the loss that we saw in logistic regression. And so the nice thing really is you can actually, once you understand these loss functions and the properties and the regularizers and so on, you can really mix and match. And kind of for a particular problem, assemble the machine learning algorithm that's best suited for you. So the nice thing about the log loss is that it's pretty, behaves pretty well in terms of outliers, actually similar to the Hinge loss. But then, one thing that's very sweet here is that actually you get these well-calibrated probabilities. So if you actually use, say, p of y given x equals 1 over 1 plus e to the minus y hw of x, then these are actually well-calibrated probabilities, which is very nice. There's a confidence estimate of how sure are you that a certain class is classified as 1 or minus 1. All right, let me show you two more. Maybe I draw here. So one is the exponential loss. So exponential loss is just e to the minus hw of x times y, which is exactly what's inside the log here. So this is the exponential loss. We will visit this. This is a big part of the algorithm called AdaBoost, which is one of the most popular machine learning algorithms. It has some very nice properties. So the exponential loss is kind of a little bit of, like if you make any tiniest mistakes, right? Like any point gets misclassified. This is e to the, you're raising this to the, exponentiating this. So this is kind of the loss that loses its nerves, right? Like if anything goes wrong a little bit, it just freaks out at you, right? And it will move the entire decision boundary, right? Just to get one little outlier right? Because the loss of getting 1 point wrong is so tremendously large, right? If this here is positive, so these two don't match in sign, this just blows up so ridiculously quickly, right? That it makes sure that no single point gets misclassified. If you don't have noisy data, then that's a good thing to do. And it can, in terms of AdaBoost, you will see, it will give us very good guarantees that, for example, the algorithm converges very quickly. Or actually gives you zero training error very quickly. The downside is if you have noisy data, it just, it blows up in your face typically. The final loss function is one that we've already seen. That's the 0,1 loss. And so you all know this one. This is delta of hw of xi does not equal yi. And that's just a 1 or a 0. So the delta function is just a 1 or 0. That's the function that basically just defines the training error. In practice, you cannot approximate it, or you cannot minimize it. But it's still important because that's typically how we measure the training error. Okay, what I want you to do is, you have a little field below you, I hope, on your notes. I want you and your neighbor to spend a couple minutes and try to sketch each one of these functions just to get some intuitions what they look like. And I would like you to sketch it in terms of z, which I think on the sheet I called x, equals hw of xi times y. So if you, right, so what's the loss in terms of z? So if z becomes large, z becomes small, if z is 0, how would you draw each one of these loss functions? So please put in the hinge loss, logistic loss, exponential loss, and 0, 1 loss. Who is ready with all of them? Raise your hand. Oh, come on, guys. Okay, I'll give you a few more minutes. Once you're done, please think about the two questions below. Which functions are strict upper bounds on the 0, 1 loss? Actually, ignore the strict, or just upper bounds on the 0, 1 loss. What can you say about the log loss and the hinge loss as z goes to minus infinity? All right. So maybe, can someone describe, let me start with the 0-1 loss. What does that look like? Yeah?
1 everywhere it's negative, and then 0 everywhere it's positive.
That's correct. How about the hinge loss? Yeah?
So it intersects with the 0-1 loss at the point 0-1 and it's a negative line.
That's right, exactly right. And this, let me just show all of them. So this is the answer. So 0-1 loss here, whenever y times h of w is positive, that means I get it correct, and the loss is 0. The moment it gets negative, it has a loss of 1. Right? And this here is a point of discontinuity here. The hinge loss is the red line. The red line has 0 loss when it's correct and greater equal 1. Right? That's very important. And so the moment you get too close to 0, like there's basically a danger of misclassifying it. This here is the margin, right? So what's happening here is when you're really far out, it doesn't care about you, right? You're correct, you're not contributing to the loss. But the moment you're getting too close to the hyperplane, this here is when you're right on the hyperplane. When you're too close to the hyperplane, the loss goes up, goes up, goes up, goes up, right? And the moment you cross the hyperplane, it keeps going up linearly, right? So this is exactly what pushes it out. If you think about it, like, what's going to happen, the points get pushed up until they reach exactly this distance of 1, which is exactly the white line that I drew earlier in the pictures. Okay, so it tries to push everything out from there. Then we have the exponential loss. What does the exponential loss do? The exponential loss is really, really aggressive, right? So if you get it wrong, like the hinge loss, it's like if you get it wrong, well, that's bad, right? And you have a large loss. But if you could instead improve another point and move it down here, or you have one point up there that you move to the right, it doesn't really make any difference, right? So the exponential loss, here you can see how it freaks out, right? This point here at -2, right, is somewhere up here, right? So if you can improve this point just a little bit, and move a little bit to the right, move a little bit towards the hyperplane, the loss is going to drop tremendously, right? So what it will do, it will try to do everything possible to get this one point right that's really far away. Right, so the exponential loss will always focus on the point that's kind of most misclassified, right? And adjust its hyperplane accordingly. Whereas the hinge loss kind of focuses on the close points, right? And kind of moves them out here. For the exponential loss, these points don't matter very much because they're so insignificant compared to, like, by the way, you don't have to look at the absolute loss. You have to look at if I move a point to the right, how much does the loss go down? That's really the important part, right? So here I can move the loss down a lot if I go a little bit to the right because it drops drastically. Where if I move here to the right, the exponential loss doesn't go down very much at all. And then the log loss is this black line here. That's kind of, that's the most chill in some sense. But that's the same thing. The one thing about the log loss is it's not an upper bound of the 0-1 loss. So one thing is with all these other loss functions, you compute the loss, the hinge loss and the logistic loss, and if you know that the loss divided by n, let's say, is 0.2, right? Then you can't have more than 20% points misclassified, right? Because it's an upper bound of your 0-1 loss. The logistic loss that's not the case, right? Sometimes it's very nice. So, but in all the cases, for example, hinge loss, exponential loss, if you drive it down to close to 0, then you must have every single point correctly classified. Last lecture was what happens with the logistic loss or log loss and the hinge loss as z becomes very negative. One thing you can see here, these two basically become parallel lines. So also the hinge loss is more aggressive here. It's at some point actually, for points that are really, really misclassified, the penalty is just linear. So actually they're both very well behaved when it comes to outliers. All right, and we will continue this on Monday.